Welcome to the city. This is the first location in the city. It's, of course, the tourist office where everything starts. And normally I do that in class with students so that they can ask questions and they can figure out how things will work in this long unit. Unfortunately, this year we have to do it using a screencast. So this section is going to be about direct proofs. Direct proofs are the first proof technique that we will learn. It's called direct because we go directly from P to Q. If P, then Q, we go step by step from P to Q. Before showing a few examples, we need two definitions that are going to be very important in the upcoming weeks. An integer n is something if there exists a in Z such that n equals 2a. You may or may not have guessed what it is. It's not that obvious to guess when you have never seen the definition, but after you see it, you're like, oh, of course. An integer n is even if there exists another integer such that n equals 2a. 6 is even because it's 2 times 3. 10 is even because it's 2 times 5. Secondly, an integer n is odd if there exists an integer a such that n equals 2a plus 1. So every time you have an even number, you can write it as 2 times a, knowing that a is in Z, and every time a number is odd, you can write it as 2a plus 1, or 2b plus 1, or 2k plus 1, with a, b, k being integers, an integer. For our first proposition here, for the proof, we will start with an example that's rather easy. If x is odd, then x squared is odd. Before we go on to prove it, we'll look at two examples, even though I'm sure you've done it in your head already. For example, if x equals 9, then x squared equals 81. That seems to make sense. And secondly, if x equals negative 5, then x squared equals 25. Here too, it makes sense. Notice that negative 5 is an odd number. Negative numbers are even or odd, no problem. In fact, we can just look at the definition. Negative 5 is 2 times negative 3 plus 1. Also, 0 is an even number. And again, we can look at the definition. It's 2 times 0, so it's even. So what about the proof? Direct proofs, we will start at P. This is a conditional statement. If P, then Q. So we start by assuming that P is true. Suppose x is odd. Then that means that x equals 2a plus 1 for some integer a. In turn, we can write that x squared is 2a plus 1 squared, and if we expand, we get 4a squared plus 4a plus 1. And here, because we want to show that x squared is odd, we have to make it match with the definition of odd. And the definition of a number being odd is that it's 2 times something plus 1. So in the last step here, I rearrange this as 2 times 2a squared plus 2a plus 1. Therefore, x squared equals 2b plus 1 for some b in Z. In fact, I don't specify it, but b in this case is 2a squared plus 2a, and we can be sure that 2a squared plus 2a is an integer because a is an integer. Therefore, x squared is odd, and we have completed the proof. When we finish a proof, we can typically put a little square or rectangle at the end on the right to show that this is the end of the proof. It's quite convenient. I remember in university when teachers didn't do that, sometimes it was a little confusing when something ended and the next thing started. Proposition 2 is similar, but might not be as obvious. If x is even, then x squared minus 6x plus 5 is odd. We're going to go through exactly the same kind of steps. Suppose x is even, then x equals 2a for some integer a, and I can substitute x equals 2a. Because this time it's a little longer, I decided to nicely align the equal signs vertically. X squared minus 6x plus 5 equals 2a squared minus 6 times 2a plus 5 equals 4a squared minus 12a plus 5. And here again, I need to match the definition of an odd number because that's what I'm trying to prove. It's equal to 2 times 2a squared minus 6a plus 2 plus 1. The only difficulty in this last step is this plus 2 here. We're taking the 5 and we're making it 2 times 2 plus 1. So in the end, yes, it's equal to 2b plus 1 for some integer b, and therefore we've reached the conclusion x squared is odd. So these are two examples of proofs using direct proof. Direct proofs are not always the most efficient. The following two propositions show situations where it is slightly clumsy to use direct proofs. We will discuss other methods in further locations. So this is what I'm skipping in this screencast. In class, we go over these proofs using direct proofs, and it is rather clumsy and annoying, and it's kind of counterintuitive. It's not necessary that we do that, because in a couple of weeks we will be able to prove these two propositions with much better techniques using things that we will discover in other locations. So skipping this is really not missing anything. We will just delay the learning until a few weeks later. So importantly, direct proofs should always have the following setup if we try to prove if P then Q. Either you write suppose P and then you take your steps and you reach therefore Q, or you assume P is true, step, and you say we've shown Q, and so on. There's other ways. I said either or, and I shouldn't have. But you have to make it clear. Proofs is a lot about communication in math, so you want to be very explicit about what you do to not let the reader be hanging and wondering what's going on. So these are two samples of how you can start and end a proof. There's more. So what are a couple of strategies that we will use when we do a direct proofs? Well, you have to use the definitions. That's important. You have to use good algebra. If you have used a proposition, then you can use the result in the next proposition. And there's obvious stuff as well, that it's difficult to make the line between what's obvious and what's not, because, well, you can always question deeper and deeper, but I think it's going to be pretty clear in this class when something is obvious and you should assume it, and when something is not obvious and you have to prove it. All right, thank you.